Let us discuss modes in a linear system. This is an important idea, particularly when we analyze linear time invariant systems, and we would like to see what is the natural behavior of the system. So, often when we do measurements, given a sequence of output data from a system, one is interested in modeling the signal as the output of a linear time invariant system and analyzing the spectral content or spectral properties. So, throughout this discussion we will assume that the input signal or the forcing signal is essentially deterministic, and one can extend these to random signals as necessary, and the spectral content is linked to system modes. So, the system modes basically determine where there are peaks in the spectrum, right. I mean, these you can think of them as eigenmodes or characteristic modes. Now, let us analyze this from the standpoint of view of difference equations, and things become very clear for us. Okay. But before we begin, a little bit of motivation why these things are very useful. So, imagine an application where you have an oil refinery and you have to figure out perhaps where, at what point in the ground, at what depth in the ground within the earth you get oil or some minerals, etc. So, people might send impulses essentially to the earth. They may get the reflectivities from various layers in the earth, and based upon the signals that are captured and certain properties of the earth layers in terms of the reflection coefficients, etc., etc., one can come up with some estimate of where the oil can be found or where certain minerals can be found, etc. So, this is basically done through sending an impulse or a shock wave through the ground, right. And another good example for modeling this is the vocal tract model. So, if you have an impulse that is given to one end of this filter, basically if you can think about your vocal tract, that can be discretized as discretized and thought about as having sections of these acoustic filters which are coupled to each other, right, and giving the impulse at one end, going through this set of filters you can get actually speech. So, if you were to model these carefully, then you can kind of think about such modes. I mean, what are the natural modes in which the system will resonate towards, right. And let us see this from the linear systems angle. So, let us take an example. Suppose we have a difference equation given by y of t plus 2 plus a1 y of t plus 1 plus a2 y of t equals 0. So, you have to realize the connection between mathematical abstraction and in practice, right. I mean, practical systems do not tell you that this is the governing equation, it is for the modeling people to figure out what is the right model that can fit observed data. So, in that sense we have to develop the theory and advance the modeling ideas forward, so that we can match reality as closely as possible. So, hypothetically let us assume in one case we have this difference equation. This is a homogeneous second order system. Okay. Now, if we take the z transforms on both sides of equation 1, we get a characteristic equation given by z square plus a1 z plus a2 equal to 0. I mean, if you take the z transforms, you will have this times z square plus a1 z plus a2 times y of z is 0, but y of z is not equal to 0, therefore this has to be 0, right. Z square plus a1 z plus a2 has to be 0. Now, the z can be solved, it is a quadratic, so therefore it is minus a1 plus minus square root a1 square minus 4a2 upon 2. So, you have two solutions, P1 which is minus a1 plus square root of a1 square minus 4a2 upon 2, and you have P2 which is minus a1 minus square root of a1 square minus 4a2 upon 2. That means you can write z square plus a1 z plus a2 as z minus p1 times z minus p2. Now, we have two cases. Case A, when p1 is not equal to p2, we can write y of t is some constant c1 times p1 power t plus c2 times p2 power t for times greater than or equal to 0, and c1 and c2 can be determined from the initial conditions. Right, I mean you know what y0 is, what y1 is, just plug in and then you can have two equations for solving the unknowns c1 and c2. Now, case B, p1 equals p2, that means you have a repeated root, then y of t is c1 plus c2 times t times p of t, where p is the identical pole, which is p1 equals p2. So, this is basically from our theory of ordinary differential equations. So, differential equations you can think about the similar analog to difference equations, and from which you can build up this theory. Now, let us consider an example here. Suppose we have a mixture of two sinusoids and observations are noise free. Okay, we have a mixture of two sinusoids and observations of are noise free. We have y of t equals a1 cosine omega 1 t plus a2 cosine omega t, omega 2 times t. Okay. So, a cos or a sine is the same except that there is a phase shift of pi by 2. So, I think without making a fuss here, I just write cosine. I could put sine as well, it is not a big deal. Now, we need to determine the mode frequencies. Okay, we need to determine the mode frequencies and we need to figure out how many observations we need. So, at a first glance it looks like, yeah, possibly there are only two modes, right. You have two frequencies, two modes, that is a wild guess one can take, but it is not. The reason is as follows. If you carefully look at what cos omega I t is, I equals 1 comma 2. So, let us say cos omega I t, this is basically e power j omega I t plus e power minus j omega I times t divided by 2. We have two phasors, e power j omega t and e power minus j omega t, right. I mean, one is going in this direction, the other is going in this direction, and this is giving you the standing wave here, right. So, each cos omega I t has two modes. Therefore, you have two such frequencies here, omega 1 and omega 2. This implies y of t is governed by a fourth order difference equation, right. Two modes for omega 1, two modes similarly for omega 2, 2 plus 2 is 4. So, therefore, we have 4 modes. So, with this let us set up the recursive equation, right. We can say y of t plus summation I going from 1 to 4 C I y of t minus I equals 0. Now, let us expand this in matrix form. So, we have 4 unknowns, which are C1, C2, C3 and C4, right. So, if I take Y4, Y4 is minus C1 times Y3. So, this is a minus Y3 minus C1 times Y3 minus C2 times Y2 minus C1 times minus C1 times Y3 minus C2 times Y2 minus C3 times Y1 minus C4 times Y0 and so on. So, if you just sort of populate the entries like this, the last would be, so if you have measurements Y4, y5, y6, y7. I get this in matrix form as follows, right. I mean, if you just rewrite this equation slightly, you will get this. It is not too difficult. I will just show you one term, one sample calculation. So, y4 plus expand this out, C1 times y, when I equals 0, this is 4 minus 1, which is 3, plus C2 times y2 plus C3 times y1, right, plus C4 times y0, this is equal to 0, so on and so forth. I mean, I am just expanding this equation and putting this in matrix form. So, assuming this the set of equations are full rank, right. I mean, this is a 4 by 4 matrix, assuming this is full rank, then you can solve for the tuple C1, C2, C3 and C4 towards the solution. And if you wonder how many measurements we needed, we need 8 measurements for determining 4 modes. This is very important. In general, we have n modes in the system, we need 2n measurements, right. So, what is the take home from this lesson? Erase this, this has to be a y3. The take home from this lesson is often we are given measurements, this is what you get, and observations can be noisy. Here I have taken a very simple case because this is the very beginning of the course. I have just taken a deterministic signal which is non-random, right. So, given a deterministic system, we want to figure out the system modes. To compute the system modes from the measurements, we have to formulate a difference equation, and this gives you an example how we can formulate a difference equation and then arrive at computing the system modes. Okay. From the difference equation, then we solve for the roots and then we can get the system modes. I will give you some homework exercises that will help you understand this module better. First exercise, what are the modes for the linear ramp? Again I assume noise free. I give you a sequence which is 0, 1, 2 dot dot dot, right. This is a linear ramp. Now I am asking you what are the system modes for this signal. Next, repeat problem 1 for the signal or the sequence 1, 3 by 4th, 3/4, half, 5/16 dot dot dot. I give you 4 measurements. Can you compute the signal modes? The last is develop a simple MATLAB model for the generalized mixture of sinusoids experiment with your choice of frequencies can you determine the amplitudes and the phases from the initial conditions, right. Basically I give you a mixture which is like this, ai cosine omega I t plus theta I equals 1 to some n, develop a simple MATLAB model for analyzing the system modes of the generalized mixture of sinusoids with amplitudes and phases. Okay, so these are some exercise problems which can help you analyze the material taught in the class and then ponder slightly on this. Okay, we will stop here.